Models and examples. Non-atomic selfish routing. To introduce non-atomic selfish routing games, we record the essential features of Pigau's example. Example 17.1 and figure 17.1. First, we are given a network describing the routes available to the players. In Picau's example, there are two parallel routes, each a single edge, that connect a source vertex S to a sink vertex T. Each edge has a cost that is a function of the amount of traffic that uses the edge. We assume that selfish players choose routes to minimize the cost incurred. In an equilibrium outcome, all players choose a path of minimum cost. In the equilibrium in the Picard example, all players choose the second edge and the cost of this edge in this outcome is 1. More generally, a selfish routing game occurs in a multi-commodity flow network or simply a network. A network is given by a directed graph G equals to VE with vertex set V and a directed edge set E together with a set S1, T1, S2, T2, etc. until SKTK of source sink vertex pairs. We also call such pairs commodities. Each player is identified with one commodity. Note that different players can originate from different source vertices and travel to different sink vertices. We use Pi to denote the Si, Ti paths of the network. We consider only networks in which Pi is not empty for all I, and define P equals to the union of Pi for all index I starting from 1 to k. We allow the graph G to contain parallel edges, and a vertex can participate in multiple source sink pairs. We described the routes chosen by players using a flow, which is simply a non-negative vector indexed by the set P of source sink paths. For flow F and a path P in Pi, we interpret Fp as the amount of traffic of commodity I that chooses the path P to travel from Si to Ti. Traffic is inelastic in that there is a pre-described amount Ri of traffic identified with each commodity I. A flow F is feasible for vector R if it routes all of the traffic for each I, which is chosen among the set 1 to 3 until k. Sigma of Fp, summing for all index P in Pi, is equal to Ri. In particular, we do not impose explicit edge capacities. Finally, each edge E of the network has a cost function Ce, which maps from the domain of R plus to the range of R plus. We always assume that cost functions are non-negative, continuous, and non-decreasing. All of these assumptions are reasonable in applications where cost represents a quantity that only increases with the network congestion. Delay is one natural example. When we study the price of anarchy in section 18.4, we also explore more severe assumptions on the network cost functions. We define a non-atomic selfish routing game, or simply a non-atomic instance, by a triple of the form GRC. Next, we formalize the notion of equilibrium in non-atomic selfish routing games. Define the cost of a path P with respect to a flow F as the sum of the costs of the constituent edges. That is, Cp of F is equals to sigma, summing for all E in P of C of Fe, and where Fe is equals to sigma, summing for all P in P such that E is in P of Fp, and denote the amount of traffic using paths that contain the HE, Since we expect selfish traffic to attempt to minimize its cost, we arrive at the following definition. Definition 18.1 Non-atomic equilibrium flow. Let F be a feasible flow for the non-atomic instance GRC. The flow F is an equilibrium flow if, for every commodity I, which is in the set 1 to 3 until k, and every pair P to the wave, which is in Pi of SITI paths with Fp greater than 0, Cp of F is less than or equal to Cp wave of F. And in other words, all paths in use by an equilibrium flow F have minimal possible cost given their source sink and the congestion caused by F. In particular, all paths of a given commodity used by an equilibrium flow have equal cost. Section 18.3.1 proves that every non-atomic instance admits at least one equilibrium flow, and that all equilibrium flows of a non-atomic instance have equal cost. In Picard's example, routing all of the traffic on the second link defines an equilibrium flow. Only one path carries flow, and the only alternative has equal cost. Splitting the traffic equally between the two links defines a flow that is not an equilibrium flow. The first link carries a strictly positive amount of traffic and its cost is 1, but there is a strictly cheaper alternative, the second link, with cost 1/2. Remark 18.2. Our description of non-atomic selfish routing games and their equilibria does not parallel that of simultaneous move games in Chapter 1. For example, we have not explicitly defined the set of players, while more general types of non-atomic games are frequently defined explicitly in terms of player sets, strategy profiles, and player payoff functions. Selfish routing games possess special structure. In particular, the cost incurred by a player depends only on its path and the amount of flow on the edges of its path rather than on the identities of any of the players. Games of this type are often called congestion games. Because of this structure, it is sufficient and simpler to work directly with flows in non-atomic selfish routing games. When we quantify the inefficiency of equilibrium flows in section 18.4, we consider only the utilitarian objective of minimizing the total cost incurred by traffic. Other objectives have been studied, see section 18.6, precisely since the cost incurred by a player choosing the path P in the flow F is Cp of F, and Fp denotes the amount of traffic choosing the path P. We define the cost of a flow F as C of F is equals to sigma, summing for all P in P. P in fancy P of Cp of F times Fp, that is the cost incurred by the player choosing the path P in the flow F times the amount of traffic choosing the path P. So expanding Cp of F as sigma summing for all E in P of the term Ce of Fe and reversing the order of summation in 18.1 gives a useful alternative definition of the cost of a flow. That is, C of F is equal to sigma summing for He in the H set E of the term Ce of Fe times Fe, and for an instance GRC we call a feasible flow optimal if it minimizes the cost over all feasible flows. As in Chapter 17, the price of anarchy of a non-atomic selfish routing game with respect to this objective is the ratio between the cost of an equilibrium flow and that of an optimal flow. We can use the cost of an arbitrary equilibrium flow in lieu of that of a worst equilibrium flow. we can check comparison between the chapter 17, since all equilibrium flaws of a non-atomic instance have equal cost. Section 18.3.1. In Pigao's example, the equilibrium flaws routes all of the traffic on the second link and has cost 1. As we will see in section 8.3.1, the optimal flow splits the traffic equally between the two links and has cost 3/4. The price of anarchy in Pigao's example is therefore 4/3. We conclude this section with two more important examples of non-atomic selfish routing networks. So in figure 18.1 is a non-linear variant of Pigao's example 18.3, with S and T, the source and sink, and also two directed edges pointed from S to T parallelly. And the first edge has cost C of x equals to 1. The second edge has cost C of x equals to x to the p. So example 18.3, non-linear Pigao's example. The inefficiency of the equilibrium flow in Pigao's example can be amplified with a similarly minor modification to the network. Suppose that we replace the previously linear cost function C of x equals to x on the lower edge with the highly nonlinear one, C of x equals to x to the p for p large. That is figure 18.1. As in Pigao's example, the cost of the unique equilibrium flow is 1. The optimum flow routes a small epsilon fraction of the traffic on the upper edge and has cost epsilon plus 1 minus epsilon to the p plus 1, where epsilon tends to 0 as p tends to infinity. Precisely, section 18.3.1 shows that epsilon is equal to 1 minus p plus 1 to the minus 1 over p. As p tends to infinity, the cost of the optimal flow approaches 0 and the price of anarchy grows without bound. Exercise 18.1 shows that this rate of growth is roughly p over ln p as p goes to infinity. And while the price of anarchy in our final example is no larger than in Pigao's example, it is arguably a more shocking display of the inefficiency of equilibria in selfish routing networks. Example 18.4, Brace's paradox. Consider the 4-node network shown in figure 18.2a. There are two disjoint routes from S to T, each with combined cost 1 plus x, where x is the amount of traffic that uses the route. Assume that there is 1 unit of traffic. In the equilibrium flow, the traffic is split evenly between the two routes, and all of the traffic experiences 3/2 units of cost. Now, suppose that in an effort to decrease the cost encountered by the traffic, we build a zero-cost edge connecting the midpoints of the two existing routes. The new network is shown in figure 18.2b. What is the new equilibrium flow? The previous equilibrium flow does not persist in the new network. The cost of the new routes S to V to W to T is never worse than along the two original paths, and it is strictly less whenever some traffic fails to use it. As a consequence, the unique equilibrium flow routes all of the traffic on the new route because of the ensuing heavy congestion on the edges S, V, and W, T. All of the traffic now experiences 2 units of cost. Brace's paradox that shows that the intuitively helpful action of adding a new zero-cost edge can increase the cost experienced by all of the traffic. So, figure 18.2, Brace's paradox, the addition of an intuitively helpful edge can adversely affect all of the traffic. So, A, the initial network, and B, the augmented network. We have a different one. The initial network, the setup is as follows. S has an directed edge to V, with cost C of x equals to x, and S has a directed edge to W with cost C of x equals to 1, and then starting from V, there's another direct edge to T with the cost C of x equals to 1, and from W, there's another directed edge to T, the sink, of the cost C of x equals to 1. That means from S to V to T has C of x equals to x and C of x equals to 1 two edges, and also another one is with a reversed order, C of x equals to 1 and C of x equals to x. Now for the augmented network, if we add directly of a route starting from the direct edge from V to W with C of x equals to 0, then from Brace's paradox, addition of an intuitively helpful edge can adversely affect all of the traffic. Now Brace's paradox also has remarkable analogues in several physical systems. See section 18.6 for details. The optimal flow in the second network of example 18.4 is the same as the equilibrium flow in the first network. The price of anarchy in the second network is therefore third, the same as that in the pGauss example. This is not entirely a coincidence. In section 18.4.1, we prove that no non-atomic instance with the cost functions of the form ax plus b has a price of anarchy larger than 4/3. While this chapter does not explicitly study Brace's paradox, we obtain bounds on the worst case severity of the paradox as a consequence of our results on the price of anarchy. Remark 18.22. Now, atomic selfish routing and atomic selfish routing game or atomic instance is defined by the same ingredients as a non-atomic one. A directed graph G equals to VE, K source sink pairs S1T1, and so on to SKTK, a positive amount Ri of traffic for each pair SITI, and a non-negative, continuous, non-decreasing cost function CE, which maps from R plus to R plus. For each edge E, we also denote an atomic instance by a triple. GRC, the intuitive difference between a non-atomic and an atomic instance, is that in the former, each commodity represents a large population of individuals, each of whom controls a negligible amount of traffic. In the latter, each commodity represents a single player who must route a significant amount of traffic on a single path. More formally, atomic instances are finite simultaneous move games in the sense of Chapter 1. There are k players, one for each source sink pair. Different players can have identical source sink pairs. The strategy set of a player I is the set pi of SITI paths, and if a player I chooses the path P, then it routes its Ri units of traffic on P. And a flow is now a non-negative vector indexed by players and paths with fp to the I, denoting the amount of traffic that player I routes on the SITI path P. A flow F is feasible for an atomic instance if it corresponds to a strategy profile. For each player I, fp to the I equals to Ri for exactly one SITI path and equals 0 for all other paths. The cost Cp of f of a path P with respect to a flow F and the cost C of f of a flow F are defined as in section 18.2.1. An equilibrium flow of an atomic selfish routing game is a feasible flow such that no player can strictly decrease its cost by choosing a different path for its traffic. Definition 18.5. Atomic equilibrium flow. Let F be a feasible flow for the atomic instance GRC. The flow F is an equilibrium flow if for every player I which chosen among the set 1 to 300k and every pair P to the wave which is in Pi of SITI paths with fp to the I is greater than 0, then Cp of f is less than or equals to Cp wave of f of wave, where f of wave, f to the wave, is the flow identical to f except that fp to the wave of I is equals to 0, and fp wave to the wave of I, that is f wave of p wave to the index I is equals to ri. And we have defined the equilibrium flows to correspond to pure strategy Nash equilibria. See chapter 1. Flows corresponding to mixed strategy Nash equilibria have also been studied, see section 18.6. But we will not consider them in this chapter. While the definitions of non-atomic and atomic instances are very similar, the two models are technically quite different. The next example illustrates two of these differences. First, different equilibrium flows of an atomic instance can have different costs. As claimed in section 8.2.1 and proved in section 18.3.1, all equilibrium flows of a non-atomic instance have equal cost. Second, the price of energy in atomic instances can be larger than in their non-atomic counterparts. The following atomic instance has Fi cost functions of the form ax plus b, and its price of energy is 5/2. In every non-atomic instance with a Fi cost functions, the price of energy is at the most 4/3. Section 18.4.1, we call this the AAE example, after the initials of its discoverers. See section 18.6. Example 18.6, AAE example. Consider the bidirected triangle network shown in figure 18.3. We assume that there are 4 players, each of whom needs to route 1 unit of traffic. The first 2 have source U and sinks V and W respectively. The third has source V and sink W. And the fourth has source W and sink V. Each player has 2 strategies, a 1-hop path and a 2-hop path. In the optimal flow, all players route on their 1-hop paths and the cost of this flow is 4. This flow is also an equilibrium flow. On the other hand, if all players route on their 2-hop paths, they will obtain a second equilibrium flow. Since the first 2 players each incur 3 units of cost and the last 2 players each incur 2 units of cost, this equilibrium flow has a cost of 10. The price of energy of this instance is therefore 10/4, which is equals to 2.5. Exercise 18.2 explores variants of the AAE example. Next, we study the even more basic issue of the existence of equilibrium flows. Recall that equilibrium flows for atomic instances correspond to pure strategy Nash equilibria, which do not always exist in arbitrary finite games. See chapter 1. Do they always exist in atomic salvage routing games? Our second example answers this question in the negative. Now for the figure 18.3 is an AAE example, example 18.6 that we just described. In atomic instances with Fi cost functions, different equilibrium flows can have different costs and the price of energy can be as large as 5/2. Now from U to V there is a pair of edges back and forth, that is from U to V, and also there's another edge back to V to U. The same thing happens between the pair from U to W and between the pair from V to W. So that means there's 6 edges bidirectional of this triangle. And the cost from U to V is X. The cost from V to U is 0. The cost from U to W is X. Again, the cost from W back to U is 0. The cost from W to V, and also the same, the cost from V back to W, both of them are of cost X. Okay, now the pairs. The pair S1 is on U, T1 is on V. The pair S2 is on U, T2 is on W. The pair S3 is on V, T3 is on W. The pair S4 is on W, and T4 is on V. That means among these 3 vertices, there are 4 different sink in the source pairs. Example 18.7 Non-existence in a weighted atomic instance. Consider the network shown in figure 18.4. Extend this network to an atomic salvage routing game by adding two players, both with source S and sink T, with traffic amounts R1 equals to 1 and R2 equals to 2. We claim that there is no equilibrium flow in this atomic instance. To prove this, let P1, P2, P3, and P4 denote the paths S to T, S to V to T, S to W to T, and S to V to W to T respectively. The following four statements then imply the claim. 1. If player 2 takes path P1 or P2, then the unique response by player 1 that minimizes its cost is the path P4. 2. If player 2 takes path P3 or P4, then the unique best response by player 1 is the path P1. 3. If player 1 takes the path P4, then the unique best response by player 2 is the path P3. 4. If player 1 takes the path P1, then the unique best response by player 2 is the path P2. We leave a verification of 1 to 4 to the reader. On the other hand, section 18.3.2 proves that every atomic instance in which all players route the same amount of traffic admits at least one equilibrium flow. We call instances of this type unweighted. Example 18.6 is an unweighted instance, while example 18.7 is not. Now let's take a closer look of the figure 18.4, an atomic instance with no equilibrium flow. In example 18.7, you can imagine the following graph. It's like you put a triangle where the triangle with a middle additional vertices V, and also the vertices of the triangle are S, T, and W, and there are edges. So first, let's describe the edges that going from nodes toward the middle of the triangle. From S to V, there's a cost function 3x squared. From V to T, the cost is x squared plus 44, and from V back to W, there's another cost of 6x squared. And then from S to W is x plus 33. From S to T, there is a 47x, and from W to T is 13x. This is an atomic instance with no equilibrium flow.